Okay, so the structure I was about, I'm sure waveguides. Angular object. Sometimes it's got to do one direction. And on the right, one thing going to be here we connect the the left of the interface. Can you hear me now?
Does that work better? Would you hear us more clearly? I mean, maybe it's on position on most places. Here, if I stand here, better. Yes, okay, right. Okay, I just stand here. Okay. What I did is I changed the microphone to use the microphone for that thing. Right. Okay. If it goes again, feel free to jump in. Okay, so this when you declare a massive idea of waveguides, thousand papers that have used along the line. This thing, it's a very widespread and effective strategy for guiding wave energy. There's maybe features for me. Thank you. We'll just jump back to the slides. I missed. I'm just going to clarify use of the word metamaterial. So if anyone has not seen a metamaterial before, broadly speaking, I mean, broadly speaking, when I'm using this word in my title, I'm referring to structured materials. So Wikipedia's definition, then some easy. More the wavelength, it's smaller wavelength with the basis class and doesn't matter at the moment. And then the other two main authorities I have in mind for metamaterials would be here, and then the UK Metamaterials Network. Our working network we set out to try and write down a concise definition for what a metamaterial was. We ended up with quite a long definition for what a metamaterial was. This was all, but usually first sentence usually got properties coming from structure. And famous examples, negative diffraction, flat lensing, and focal devices to the fields and seismic structures, applications of antennas, energy harvesting, commercial applications. And more about metamaterials and metamaterials. Enough about that. So, really, when I'm talking about these metamaterial by problems, as a petition, really what I have in mind is something like the following. And these are the two schematics of the two problem settings that I'll talk about. The first half of the talk will be top. This is the sketch of a three-dimensional gassing problem. We're solving a Helmholtz problem in 3D. Got some material inclusions. That will be highly contrasting, taking cross. So the full differential problem in a moment. And then the second half, we'll move on to quasicrystals. We jump down to a 1D problem. We're studying transmission through some one-dimensional system. And crucially, I've got some patterns of A's and B. A and B just two different types. The range are A's and B's. That quasicrystalline ways, see if we can understand. We'll look some theory to understand. And so this kind of summarizes why I like this metamaterials, because my background is essentially spectral analysis, and it's a really nice breeding ground for spectral analysis. Okay, so these waveguides I'm talking about, what's the one here? So briefly, so same page. Essentially, what's happening here? Like take the 1D example I had slides ago. Series of lamina by arranging in pairs. Turns out when you look at the spectrum of this object, you've got Bloch parameter on the y-axis, x-axis. When you have a regular, so fine gap between the first. That's your starting point, and then the aim is to make a perturbation that creates a localized line. Very good. So say pushing together from parts, yeah, a localized mode looks like so. Cross section, selection, guidance. Fine. And it turns out that surprisingly the frequency of that moves. So the kind of questions we'd like to ask are: can we predict which perturbations will induce these localized line modes? Can we fine-tune or the properties? I mean that without using any numerical machinery. And then lastly, in the second part, we'll use the starting material for unperturbed lines. Okay, so on the slide on Floquet-Bloch analysis, for this specialist audience, maybe just for the sake of clarifying what's in this picture. The say x-axis is what you care about, and as a result, I've formed the blue lines at the top are ranges of frequency that just exists. But crucially, blue is frequencies that can propagate through the material. It's not. And then the y-axis is this auxiliary parameter where we're decomposing the spectrum operator is posing to periodic problem by, instead of studying the periodic problem, we study the same operator posed on a unit cell with Bloch boundary conditions in these periodicity conditions. The advantage of this is that it's a new operator, this one that's boundary condition countable to spectrum, it's band straight out. Okay, so let's really get into it. So the starting point of the unperturbed periodic material that we're going to use for the first part of this talk is like so. So I'm only doing simplicity, I'm only doing periodicity in one direction. So generalization to planar or glass disease is relatively straightforward. The differential problem I'm solving is like so. So I've got Helmholtz equation in background material. And I've got instead the Floquet-Bloch boundary condition and with radiation field. Fine. And I'm assuming that these material inclusions in the transmission problem. So I've got continuity condition, boundary of C. C is the structure. And I've also got a continuity of flux. The key thing to highlight here is this delta that appears in the continuity of flux. This is our material contrast parameter. It's going to be an asymptotic parameter.
Same number.
Exactly. Which is a assumption to make things on my slides later. Okay, so we've got our delta, and so for the acoustic case, for example, then delta would be the ratio of the density inside and outside. And so some of you would have guessed the setting that inspires this is minute resonance. Where these are air bonds, this is water, in which case density there, context.
You think of the function usually if some kind of C1, H1 or something, so saying is periodic means function and so
Okay, so as I say, this is the resonance of these structures, which happens, it's exciting because it happens in a deeply sub wavelength. Air bubbles in water resonate at a wavelength in size, and we're studying extensively by mass per minute, century, so as well as having this resonance in after him. And then the question that often comes up when I mention that physical example that's kind of motivating this level of water is how do you go about to talk about very specific arrangements of resonators in background material? How do you build that? So I always point to this paper from this guy from the University of Minnesota, where they're injecting gas bubbles into the polymer gel. Viscosity, which means that will hold their shape.
Air did this work more or less for fun.
I don't
Big man Air did this work more or less for fun.
It's
That's what the state.
yes.
Side.
Sideline is
Yeah.
being quite influential.
Yeah.
Okay, so as I said, our approach to studying this is asymptotic. So we've got our delta, our contrast parameter, that's our asymptotic. We particularly want to characterize the sub-wavelength resonance. Resonant modes occur when frequency is very small, so we're going to define our notion of being sub-wavelength as an asymptotic. Definition at the top, the kind of solution we're looking for, we want solution, a non-zero solution, mu from the Hamilton equation, and further we want that our frequency omega depends continuously on delta and converges to zero continuously.
So you're using a linear solution thing, even though the bubbles are.
Absolutely, exactly.
So when does that work?
So my understanding is that when your contrast is very, very high, while I acknowledge that the surface tension, etc., is important, my understanding is that when the contrast is sufficiently high, the pressure modes, the breathing modes, which is what then dominates. Okay, so when we bear this this definition in mind, and we do our analysis, the quantity that comes out turns out to be this capacity. And so because I want to move on quasiperiodic boundary integrals, but we're using a boundary integral for solutions. So G is the appropriate Helmholtz-Green's function. Conditions. And it turns out that the object is going to come up in the film in a second. It's this matrix which is obtained by taking, so we got in our, if you think about our structure, like so, in the unit cell we've got two objects, D1 and D2. And so as a result, this matrix C, I'm introducing as a 2x2 matrix. And to obtain it, you take the indicator function of the boundary of one of the alternatives. Then you apply the inverse of this function operator. You then integrate over the boundary of another resonator, and that gives you.
So we usually need constants matrices when you do low frequency action.
Exactly.
The original.
Yeah, exactly.
That more or less.
So can I just,
Yeah.
sorry, I should pay more attention.
Sorry.
If you've got that sum there, just on LM00, does that mean you've only got a single line of inclusions and then
Exactly. So I'm going to be presenting today a problem where these are repeated periodically in just one dimension. And actually, that's a good point. We just said I claim that the generalization to previously more than one dimension is relatively straightforward. It's done. Just done. It's modified. Okay, and so then kind of the main result underpins this contrast analysis is the following. So this says that this is two things. The first, that we define our wavelength resonance into this asymptotic condition. Then it turns out there are n of them, but n is the number of cell. Get which is 2. And with positive R, spectrum is. And then additionally, the reason that this capacitance matrix is useful is this determines the leading order behavior of these. The lambda here is the eigenvalue capacitance matrix, then the leading order term in the sort of expansion of omega and delta is given by lambda. This here, the volume denominator is the volume.
Capacity to solve the problem for any object. Number of objects in the cell.
Exactly. So in practice, when I show some numerics in minute, we'll see that it's not spherical. Okay, so we've got some. I guess my claim is this is nice because we have a nice asymptotic formula with exactly the caveat that's just been raised. The challenge is generating this thing, but simply for analysis, this is something we can deal with. Relatively straightforward, should we say? Relatively. So we can use this to start making statements about the structure. So as I said, we want to build these waveguides. Our starting point, my recipe on slide 3 or whatever. And step 1, we're going to find the structure there. So we'd like to use this symmetry result to understand when this happens. And it turns out we can show that using this formula in the slide that so long as L and L primed, we have these separation distances between objects within the unit cell, outside the unit cell. Whenever they're distinct, then there is a wavelength band which we can use. Nice. That was step 1 on this recipe that I had. Step 2 is okay, let's make perturbation to this structure in which notice.
We're talking about 3D problems.
Exactly.
Not that one.
Exactly. Three, but these are in the third dimension. It's not. Okay, so okay, we want the strategy to understand. When we start making perturbations to the structure to try and create these localized modes. of our waveguides. And we want a strategy to try and understand perturbations we make, whether or not they're one of the preeminent theories in literature revolves around this idea of topological projection, which I'll talk about briefly. So let's define the exact phase. Exact phase is a topological index you associate with picture, shell number. Crucially, it's new, and the details of that not so important. Crucially, it's a quantity which we obtain by taking these are most solution to this problem I introduced in Helmholtz problem on this unit cell with the Floquet-Bloch condition to size against dependence on alpha. You take that, you integrate it with respect to alpha, take the unit product itself, and integrate over Y star, which is the set of all possible alphas. When the problem is 0 to 2. Okay, we get some quantity that it turns out we can show depends on the relative choices of. Turns out L is less than alpha, it's only 0. And my claim is that again, I asked something that it's useful. It turned out this slightly abstract quantity is nothing less than change in argument of the diagonal entry of Pastel's matrix when you vary this possibility to effectively.
I say it doesn't really look like a phase. It's a vast theory in the background which shows that that is naturally viewed as a phase.
Yeah.
But is that something a bit new to me? Okay. If you presented me with that equation at the top,
Yeah.
I can imagine evaluating it.
Sure.
But the fact that it has a meaning, it's a phase. Is that something you can explain in a few words, or does it require a very advanced theory involving your matrix C? In a way, it looks like an ordinary inner product, isn't it? I mean,
Yeah,
it's a chain of pendulum.
Yeah, so your question was, can I explain in a few words? Well,
Right.
about it, no.
Okay.
Yes, let's do that.
Interesting work to do for me. That is absolutely. Yeah.
I'm very happy to do it. Okay, so if this is alien, then I guess you're wondering so what. The so what is there's this very extensive theory, particularly for one of these structures, very extensive theory, of which I will summarize very crudely with this primary school level diagram. Is that if you take, this is the big idea, this is what I see it as well with topological projection. If you want to form an interface that has supported localized nodes, then the strategy for doing so is if you take two different materials, they're colored with red and blue, and they're associated to different values of appropriate topological indices, and you stick them side by side. And then there's this vast theory that says that nodes will tend to be localized about the interfacing. Additionally, because of the underlying properties, so two materials are topologically different. Not only do nodes exist, they have some elements of clusters. But let's do that to understand how this stack phase depends on geometry of the structure. Let's try and build material with these lines. So I have one here, switch to spheres, use numerics. Easier. And what you can see is I've got them arranged in pairs. Then in the middle, I switch to just have one. It's the classical SSH. Which is to speak eager, famous paper. Very famous, should we say? We alternate. The crucial thing about the structure is you've got alternating short, long, short, long, short, long operation distances. And in the middle, we switch to just have short, long, short, long, long, short, long, short. And the reason that this interface fits into this theory that I'm explaining is that well, with me, let's start here, somewhere in the middle of the interface. If we move to the left, then we've got pairs that are appearing so they are close together. So you can associate them, we can start with our unit cell lines here, here. Then we have unit cell that will be associated to exactly 0. If we started here and went the other way, then we get that. So we'll use my red and blue sketch. We have red on the left and blue on the right. And indeed, when we will simulate this, exactly, this is a simulation for finite structures. We've stopped it. Finite number. That should say hope that the interface will matter. Will actually be recently this one don't matter. It's large. It's slightly useful comment. Now we get this level. Now, at the moment ago, I commented on robustness. So a very brief diagrammatic representation of that. Here I'm for this finite structure, adding on the x-axis increasingly large random errors to constituents of resonators. Distributed errors. I've covered all the localized mode. This one is in red, middle here, and the other one in black. The thing that I might need to take from this picture is that the variance that produce on this red localized mode is substantially less than black ones. The magnitude that's not. And additionally, this mode remains even for very large digital errors. This is expressed as a percentage of the average distance between resonators. Even when these are moving by 10%, it's still remaining nicely linear. Yeah.
So this is the electric sites, that particular profile event.
Absolutely. So this is an argument. This is we don't have a source here. This is us solving this resonance problem, which is no one can. It's looking for solutions that exist in the absolute set. So it's a good comment because was what I wanted to solve this. Still some in there.
So it's an arbitrary amplitude.
Exactly. Like,
So if you magnify X out around that bottom spike, that you get quite smooth.
yes.
Like a cross.
No, it looked quite smooth. The reason it looked quite smooth is just
Look at the top picture, you see first ones of waves in one of those.
exactly. So this one here is that one here.
Yes.
And in these modes, the field on within each resonator is approximately constantly the order. So the top here is the order flux.
Could you possibly remind me what position arrow sigma is?
Absolutely. So I'm trying to test the robustness of this thing. So I'm adding random errors to the position of each resonator.
All of them.
Independently, exactly.
Every single one.
Every single one.
The out by as much as 7%.
Small English with a condition to actually that. Don't get to put it together. Okay, so time is keeping lost. I'm tempted to move on, move through my other things about periodic structures quite quickly. So when I had more time, I would show you this structure where we created an interface by dislocating wave pairs. The advantage being, animation showed, as you do that, we create two locus modes, one from each side, and as the dislocation comes on from large converge to somewhere within the bandgap. And the motivation for this was that we wanted to be able to find a way to tune the properties of a structure. And a particular game we wanted to play was we were to say, okay, if you give me material with spectral gap, I want to be able to put a localized node at any point. So this is a strategy within this SSH pair stuff. I won't do. Okay, we've got to briefly show you the picture from Ron. We've been working on some experimental realizations of this. Elastic plane with bottom, so it's a very, very different system to the kind of thing that the model is for. And so the only point I wanted to make with these slides is that with this slide is that so I can allude at the start, but part of this how I see materials. Part of the idea is its properties coming from structure, right? So in essentially, to some extent, with some caveats, able to remove yourself from the specific physical setting. And so here we've got the same geometry as we had in our high contrast Helmholtz setting. We're doing the elasticity setting. Clearly, the line is very different, but turned out that it's qualitatively different. Okay, so I started by asking some questions on one of my first slides. I've answered some of them. We skip past it. Crucially, the one I have still unanswered is what can we do with the underlying material not good? So let's spend the rest of our time doing that. So now, for the rest of the talk, just to make the lives difficult, I'm going to change setting somewhat. We're no longer doing 3D scattering. We now do a 1D transmission problem because I want to do symmetries. And so the three systems examples I have in mind are spring mass spring system, compressional waves and continuous rod, and flexural waves beam, where beam is constrained up. They're all systems that have 2 degrees of freedom in edges of each piece, class. And as a result, you can 2x2 transformations to describe how the wave propagates to this. And as I alluded to at the start here, the game, the geometric game when I play, is have 2 different types of cell. So either we're varying the mass spring, we're varying the spring constants. In the rod case, we're varying either the cross section of the density. In the beams, we're varying the stiffness. 2 different types A and B, play with the pattern then see if we can understand.
So the properties vary, but the geometry remains constant.
Exactly. I mean, so actually the length could also vary. So this is true. The length of each, I've got a code in blue.
If each one was a different length, we're not talking about that as well.
No, they could be different ones. They could be different ones. It's just a one problem. So
Not use any query function.
I'm not going to use any Imperial response. I'm just going to use transforms. Kind of the idea is we're going to study how the basic structure. So my pattern of A's and B's corresponds to me multiplying corresponding pattern with TA, TB, TB transformations. So essentially, the underlying analysis is to understand
Possible phase change is correlated in the transformations. So that sense the length is
exactly. Okay, so we could, within this setting, we could do not, but we're interested in. I want to try and do some non-periodic quasiperiodic things. So I'll put an example in this direction. So two tiles. This is a pattern of A's and B's that's formed according to some tiling rule. So that is a sequence of words, should we say, so patterns of A's and B's, but it's formed by, to initiate the sequence with F1 here, I've got another so which is A, and then each subsequent iteration of the sequence is formed by taking the last two, sticking them together. So I start with A, and I've got AB, then F3 becomes ABA, 4 becomes AB, AAB, and so on. And when you go to this, we can largely sequence of also number of terms in each iteration sequence corresponding to the Fibonacci number. Yeah, and what the thing going up would be. And so this is an example of a quasicrystal. And so before I get stuck into how we understand its transmission properties, let's talk more generally about quasicrystals. So this first question you might have is, why should you care? Pretty harder, so why bother? So I've got two comments on that. So one is from this paper, it's been observed that quasicrystals have some advantageous properties. One being very large band gaps, it's a really attractive property. The second, there's quite a few references that point to the robustness. Exactly as I was showing the periodic structure a minute ago, it appears it's not well understood at all. I haven't really decided to show you exactly. It appears that the quasicrystals have some kind of robustness. The band gaps are fine, so it's not really it. Okay, yes, so it's I shouldn't say band gap, I should say spectral gap. So the range of frequencies. So in the so one big body of theory that studies spectral theorists studying spectral studies. So they usually characterize non-propagating modes being one that contains sufficient. And indeed, that kind of question is what's attacked quite extensively in this body of literature. Ask questions. That sort of thing. They ask the extent to which spectrum has Cantor-like properties, and so on. There's also worth mentioning as a direction for understanding waves and quasicrystals. But I'm not going to touch on this all today, but is use a Chatter project. Lies on the observation that these non-periodic tilings, although non-periodic, can be obtained by taking something higher dimensional, periodic, taking rational projection of this. Fibonacci, this Fibonacci pattern, you can take something 2D that's periodic, take a slice through it at the rectangle, which turns out to be one of the coordination. Like this. Similarly, Penrose tilings, 4 or 5D periodic structure projected. And so there's some promising results in this direction. So here's a figure from this paper by Johnson's group years ago, where they're doing, on the left, they just computed the spectrum for the 2D thing and then projected. Right, they've used some periodic approximation to estimate the density of states of quasicrystal. So use the spectral gaps into appear. And then, as I alluded to, really the preeminent physical literature for understanding the spectrum quasicrystal is to take supersonics, approximates. And I will claim that at least one of the contributions of the analysis that I'll show you for these one of the Fibonacci things, so our analysis gives credence to these period, proves. Okay, so let's have a look at some spectra. So here, what we're doing periodic approximations. Here we've taken the top row 0, F1, and I say read this paper. Figure I borrowed from this paper. So we're taking these unit cell F1, F2, F3, generated according to this rule, taking them as the periodic unit cell. As you work your way down, the unit cell gets bigger, it's more complicated, and as you'd expect, the spectrum gets more and more up. See, is even when you F7 here, that far through the sequence, already you've got a really complicated possible pattern of stop and pass bands. Which is Cantor like, which is very, very reminiscent of Cantor sets. We've had to try and understand that. In particular, the thing that we set out to try and understand is when you look at this picture, it's apparent that there's some quite complex things going on here, for example, and here. It's also apparent that there are some very big spectral gaps that emerge very quickly in the sequence, seem to remain pretty stable. Super line gaps to demonstrate resistance. And so the basis of our approach is there are only two resistance transfer matrices. So the idea being, if you know the solution, you use derivative at one point, you find the solution to derivative at another point, multiply the matrix. Got some pattern of A's and B's, represented by reds and blues, and just multiply the corresponding matrices for the structure. And it turns out the spectral gaps, this material, band gaps we do for approximations, are characterized by eigenvalues, matrix. And then because there's these transformations in also 7.1, then now the crucial thing for attention to is the bottom here. So frequency being a spectral gap is equivalent to trace of the corresponding transfer matrix. And this thing, because the matrix of 7.1 traces the same thing. Okay, so the point I'm making is that we want to understand the transmission spectrum of quantum materials. We just need to work out what transfer matrices, find for which frequency we correspond to. And it turns out there's a very helpful result, as you just saw. There's a helpful result in the Fibonacci setting that makes life somewhat easier. And it's an old result. I think it dates back to the early 80s from Milton. And it says that so if you have your materials arranged according to this Fibonacci sequence, then if Xn is the trace of the transfer matrix associated to Fn, so the nth iteration of this Fibonacci sequence, then the sequence of traces satisfies this recursion. Nice, because this problem, which is a second order differential problem, trying to understand the spectral gaps of it, has been reduced to studying, to asking the question, from which initial conditions is this nonlinear recursion relation remain between bounded lengths. So let's simulate a few orbits of this recursion relation. So here we've got three examples. R here is the ratio of the material parameters of B. 0.92 is changing from no reason whatsoever. Why? Unimportant. Crucially, we have three different frequencies here. What you see is that for this orbit, these parameter values, we have this recursion relation gives a sequence that, at least for 100 terms, seems to be bounded within possibilities. Conversely, let's change the frequency by a bit. In here, we have a sequence that seems to be bounded by plus or minus 2 for quite a while, but then after, in this case, 40 iterations, escapes and then seems to diverge quite quickly. And then on the right here, we've got one that plotting log scale, it seems to diverge really well. Okay, so we'd like to understand which parameter values this. Cool. So if you're anything like me, if you spend your teenage years looking at pictures of fractals on the internet, then when you see second order nonlinear recursion relation, you see pictures like this, you instantly think of the concept, which we count as the set of initial conditions for which this second order nonlinear recursion relation will be bounded. Well, we've done at first glance is bad news because this mathematicians, prominent mathematicians, spend centuries trying to understand this, but we can take inspiration from it. In particular, one It's simple to show property of Mandelbrot set is that it's bounded by a circle of these two. In other words, for this recursion relation, if it ever escapes circle of these two, then it's guaranteed to diverge. It's gone and it's not. And so looking at the pictures we have for our second order recursion relation, it would certainly be reasonable to hypothesize that the same thing is true. However, it turns out not. So it turns out you can find plotted on here, you can find orbits for our relation that in this case it's periodic, period 6, but every third value takes arbitrary measurements. These parameter values is taking values minus 2.8, 2.8, but by changing the frequency, you can make this be arbitrarily large, it turns out. Point being that it's very nice result that if it means a certain region that's going to diverge, it's not possible. But it turns out it's kind of, I would say the next best thing is possible. And that is the following result, which says that if your sequence is outside of plus minus 2, so you're in a band gap, and additionally, your sequence is growing, so you have 3 terms, all outside plus minus 2, each one is bigger than the last one, then the sequence is guaranteed to grow forever. Which guarantees it. But it's quite noted that this example doesn't satisfy this condition. And so this orbit I had from the previous slide, one that I've registered quite quickly, satisfies this condition of the 20.
See that then second. It only says that x and plus 1 is bigger than 7. So x
Absolutely.
Won't change the limit.
Absolutely. Very yes, you're right. This is
So is that the lemma, or did you write the lemma?
this is an old version of this slide. It's very much yeah, it turns out that the taking minimums, there's the ratio of these two, 1, ratio of these two being 1, and they will continue to grow with at least that exponent. Okay, and so I said we wanted to, the aim of all this was to characterize these so-called superband gaps, ranges in the frequency spectrum, Floquet-Bloch structure, which are band gaps and gaps. And this condition is what they call it. So to step back from our abstraction setting, this is saying if you have a frequency from which some point in the sequence you have this condition satisfied, then you know that for all subsequent iterations in the sequence, band gap condition will exist. And so here we have 3 physical systems: mass spring, continuous rod, and beam. On the top, we have the active pass bands and gaps. It's just to be make sure it's created, it's inverted from and before, which I apologize. It's 0 on the bottom, and the more complex as you go up. So that's in the blue, and in the red, we have these superbands. So in the red, what I'm doing is each point in the sequence, given frequency, checking whether this condition, this growth condition, holds. So what you can see is that even if you want to hear one step in the sequence, screen, we already have this range of red frequencies, looking at 3 terms, which satisfies condition to know this range of red frequencies will be in the band gap for all. And so have the frame I said at the start was in this period. It's nice for understanding these super band gaps, but I would argue also have implications for justifying the usage of periodic approximants of quasicrystals. That's what I want to demonstrate with this picture. So here I'm doing the continuous rod case. What I've taken is I've taken a really big one-sided sample of a non-periodic Oops. 8, 8. Should be slides, that's that. Which I think a big non-periodic piece of as you see. Red line is the transmission spectrum of that. Give you some axis. Now the log of the transmission coefficient x-axis. And then in each of the 4 plots, the shading is these super band gaps that's predicted by, in this case, the second being the sequence, third, fourth. What you see is that, okay, even when you get down to, say, only number 4, quite early in the sequence, the gap, the super band gaps that you predicted, quite, they're not recovering some complexities happening here, for example, so these small gaps, but the big gaps are being. So I'm claiming that if one wanted to use this large-ish quasicrystal for some kind of device, then the precise way of figuring out the main features of this transmission spectrum would be to use this. Okay, so time ticking by, so I'll wrap up quickly now. If you recall, in the periodic setting, finding the band gaps was only one part of the game. Really, what we cared about was once we've got a gap, making a perturbation that creates a new gap. In the setting of quasicrystals, our approach of doing that is to induce a mixes of structures using an archery structure to generate material to the right. As a result, we get some artificial in the middle. It's not that is very much not our idea. So there are 2 references exactly that. For in this case, they're not doing an archery, they're doing different quasicrystalline material. Here we've got an acoustic waveguide, reflected in the middle. So, yeah, studying modes that are localized in the middle. Here they've got an elastic sheet scattered on it and similar. We can speak on each on time, crucially the center of the band gaps can be understood by looking either free values. When you're within a band gap, if you want to understand which frequencies can not support localized modes, then the condition is to look at the associated values. Works with trying to make this very progress. Characterising. So look at some pictures to finish. So here I've got on the x-axis I've got the material contrast parameter, it's the ratio of the material parameters to B. So here we're doing a rod problem. I'm just varying the material parameters the same as there. I'm just varying cross section, the ratio of cross sections. Here I'm colouring, propagating those in black, gaps in white. You see that there's a complicated pattern with gaps, there's nodes. With these pictures, me playing around within a gap, I'm colouring it at this colour scale according to the number of iterations it took in order for this growth condition, number of iterations it took in order for that condition to be satisfied, which I claim, if absolutely no need for justifying it, it's probably a reasonable indicator for how quickly that moves. And so, of course, we want to get modes in this gap. So we induce make this reflection to have this symmetry. Then you get within the gaps candidate frequencies to satisfy this condition on the eigenvectors and counter matrices. So spawn localized modes. Actually, here in the same vector, which I apologize. But I'll show you the mode instead. Here are the 2 examples. I do this. It's not important now that dotted lines here, and trying to come up with a way to estimate the decay rate of these. We don't basically do multiplication of multi-scale engines. Yet to find it. So proper way of doing it. That's the question. Okay, so I learned that. So I started by posing this question: what are the quasicrystals and features using waveguides? Absolutely haven't answered yet. However, hopefully, what I conveyed is the large and growing market of multi-material technologies. Important science, but it's all based on pure structures to one extent. But quasicrystals have been shown to have some nice properties, and the main barrier to their widespread uptake is the lack of seismic effects. The properties of particular gaps, and we hope there are other things that small steps. Okay, thank you. Shows needs that it's a 2x2 matrix with determinant. So deriving the corresponding thing, say the 1 matrix.
So these spectral graphs, if I understand correctly, are they come into play due to interference.
Yeah.
So in that sense, as opposed to resonance hybridization. So in that sense, they will not be subgrid.
There's no reference.
So I would argue that that's a big limitation. Because when you
Reflection, symmetry. Yeah. One. If you propagate a wave towards that interface, does that mean that you get something corresponding to a resonance? Right? And does that have big implications for transmission? Possibly. Question. I've never thought about this. It's the symmetry distribution. It just sort of. Right. Yeah, I see your point. Yeah, I see your point. Questions?
I just have sense. Sure. In 3D. No essence of it. Just chosen to be small scatterings.
Exactly.
And you looked for the high frequency. The high frequency is real.
The item frequency,
Okay. Yes.
Yeah, so that's very important. Because when I showed you the band diagram,
So you're showing us the one that's closest to the real axis. One other question. Is that there's kind of special points at which you would get the exponential growth some kind of bang gap. So your oscillations are bound in the trace. So outside plus minus 2 at some points.
yeah, these pictures are
Later that one of the top right.
yeah.
What happens when you actually solve this problem for that kind of quasicrystal?
So let's think
I
about
understand what's going on here.
so what's actually happening here is the thing that's on the x-axis is the index of the material. And so what I'm saying here is that you have so if we take some of those, so you do an Fibonacci sequence, you form the next one by sticking the last two together.
Yeah.
So you have here this is number 4th and 5th iterations in the sequence are such that this frequency is right, not in number.
Yeah.
And then when you stick it together, you get something that isn't a number. Which is not surprising.
But then you go out of it.
But then when you stick that with something together with something that's then you're right, you've got something that's not a Langmuir and isn't a Langmuir. Together you get something. Does that make sense? So I agree with this.
So I would just say, the bang gap means that over that part of the material, you're getting some exponential pay. But then you have another bit onto it. Use that.
Exactly.
Very special
Yeah.
ways.
Exactly, and I agree with you because so when I started working on this, I thought it should be the case that, like I said, so fundamental questions are following. Right? So let's say you're doing A's and B's, A and B, whether So a single function, if A and B are both the same gap, you stick them together however you want, that's completely randomly. Does that mean, does that utility forms have a band gap at the same frequency? I kind of think that should.
Yeah.
To show that. And what we're saying here is that, okay, what happens if A has a band gap and B doesn't? Then you stick them together.
Yeah.
Does that have a band gap? And so this shows that in general, no, it doesn't.
But these are quite certain quantities.
It varies.
Yeah.
So I think it would be reasonable to say that in general, probably the rules. That's exactly the explanation. Okay.
All right, that's all the questions. Thank you again.